And this is another common kind of reaction to say, well, just replicate it. Keep an index so I can just replicate some of the information or a foreign key. But the problem is this. Now I've broken the bounded context. That is where we realize there is a third option, and that was this guy right here. Because take a look now. If I create a data domain right here, and by the way, this is only a handful of services. Like, well, wait, you're sharing data. That's exactly right. 3, 4, maybe 5 services. At most 6 services I am sharing. Why the low numbers? I got to coordinate for database changes. Number 2, usually this short of number of services are owned by the same team. We're a development team. All of you in the front row here. We're all on the same team. These are all our services. We talk to one another. We see each other every day. And so the point is we're all communicating. We can coordinate the write ownership, the read ownership, because it's all within the same team. Once those services start crossing to other development teams, this doesn't work. And so I'm kind of creating a loose bounded context around here. But I'm not duplicating the data, and I'm not having to ask for it. Now notice here's another service that needs my data. You're going to have to ask me for it. And so the point is this doesn't eliminate Interservice, but it significantly reduces it though, doesn't it? Yes. That's those data domains, and that's the point. So now we have another good way of reducing that Interservice communication.
So is CQRS also a solution in this? Because you can write a very fast read service, and
right.
write is owned by the...
It would be, as a matter of fact, a form of CQRS. As a matter of fact, not necessarily CQRS, because this, don't forget, and I'm glad you asked that, by the way, because we saw CQRS this morning with a single service, demographics, and I split it between read and write. But keep in mind, this service right here is our demographics. This is the wish list. This is the preferences in our website. 3 different kinds of services. CQRS really is about the same service and splitting up read-write. But here, one other option I do have, which we'll investigate in part 4, is I could, in fact, leverage caching as a 4th option to be able to cache that customer information across those 2 or 3 services. So instead of sharing a schema, I now have a replicated cache across those. And now, the key point here is I am breaking the bounded context a little bit, but I would have to worry about cache replication when that name changes. You know, that kind of decision, how often does a name change? Not often. And so the point is, because names don't change that often, that's probably another good solution. In other words, go back to this part right here. Go back over to here and just take the name. Now, I'm not talking about all the customer data, just the name. What do I need to really share? That name. Then cache the name here and here. And now I'm replicating the cache, but at least I don't have that communication to go get it. It's cached in memory. Okay.
So what I was saying is that like put into 2 parts the profile service.
Who's
so
talking?
one for read, one for write.
Where are you? Oh.
Yeah.
Oh, there you are.
So what I was talking about, that putting the profile service itself into 2 parts. One is for writing and one for reading, and then probably it can be the cached way, and
sure,
everybody can read from it.
Yes, exactly. Yeah. So we can start to see there's some options here available to be able to reduce some of this inter-service communication. This is, you know, this is great. This was not planned at all. This is like totally extemporaneous workshop. I love this because this is a whole topic I wasn't even going to discuss. So this is great.
Mark? So if so let's assume we cached it, we replicated the cache in all 3 microservices, and the original microservice which updates the database for the customer name. If that microservice crash, then it should not impact other services because we have the replicated cache.
That's right. We are going to get to the whole topic of caching. However, really good observation. So one of the uses of caching, and that's why I really added the whole caching piece that we're going to see in part 4, is...
I have a question.
Hold on 1 second. Is because I want to just answer this part about the caching piece. Caching gives us one additional benefit, and that's this. If I have a cache of the name right here in here. You know, the other thing is if I go and ask for data, and you're right, that demographic service crashes, and I need the name, I can't process. Hello, Noel. But if I do have a cache, at least I have some copy of that name. And so, yeah, the caching gives us an extra benefit, which is nice because the caching is going to be extremely complicated, as we're going to see. But the added benefit is I do get a level of fault tolerance. I'm working with a company right now that we are leveraging caching across data centers in order to achieve a level of availability. And we're talking about, you know, simulating a 4 nines or a 5 nines architecture, 99.999%. And when systems crash and we have to have the data, the only way to do that is to be able to cache it so that at least we have some level of operational ability.
So we have three main things.
How many microphones do we have here?
Yeah, one.
So we have three main things to look out for. First, reduce the number inter-service dependency.
Yep.
And then reduce the data point, like bringing 3 microservices together.
Yep.
And when we decide for caching, then we need to think like how we can, if one service crash, then how we can make
Right.
the other services available.
So that's right. And to kind of end this question thread, and we'll go to the next microphone, is the fact that if I do this, notice this data domain here now, for a customer, these 3 pieces of information, there's no cache here. But if this service goes down, I don't need to use caching because I've got the data. The name is here. Now, where I would start introducing caching at this point might be, and I'm getting ahead of myself because we're going to talk about this, might be if I have problems with the reliability of this database. In that case, I do have a single point of failure, don't I? I do. And that's meant I may want to have some level of caching for minimal operations to be able to continue. Where's the other microphone?
Yeah, one question. Here.
Yeah, how about a orchestration service in between in which stitches together all the information?
I'm going to talk about that in part 4. Yeah, right after the break, I'm going to talk about the orchestration service. Yeah, let's call it service orchestration pattern. Yeah, and I'll definitely talk about that.
I have a question here. So you have done the service federation here.
Oh, I'm so happy you guys are. I've got lights blinding me, so I can't really see you guys. Okay, there we go.
You have done all the services federation with the through the functions, through database, and through the request, and you have done certain level of job. And while you have been deploying the projects over a period of time, when new module comes, which need to be incorporated, which has a highly highly dependent on other data sources. So is it not going to have an extra overhead to redesign everything to again segregate it?
Absolutely. So when I do have other services coming about, that's why this is hard. And actually, what happens as our systems evolve, your question exactly is answered by this piece right here. It's that flow. And you're absolutely right. As we start introducing services, one of the things that makes microservices so hard is that this cycle just continues every single iteration. Every time we add new functionality, I need to assess. Really, it's identifying the service. Actually, it's all these steps. I need to map it to the data, and all of a sudden I find I need to start sharing data. As a matter of fact, this piece right here, do you remember when we had those 3 services all talking to the same database? It's called a data domain. When we start having 4 services, 5 services, 6 services, 7 services. Matter of fact, I'm going to illustrate that in the data piece, and so we'll hold off on that question because I want to show you what happens when we start adding services and we all of a sudden have 8, 9, 10 services sharing a data domain. It's too many. We would do service consolidation at that point. So yeah, this is a normal process. Your question exactly reinforces that this is a continual loop forever. Every new piece of functionality. And you know, this is great because you may do a perfect job in your microservices ecosystem, greenfield or migration, it doesn't matter. Perfect. And to your point, every time we start adding new functionality, if we don't pay attention to the overall architecture, it's going to become a spaghetti mess. Exactly. So this is a continual. So here's what I usually do, and this is where I can inject some experience. This happens, and it will always happen. And so will you be changing the granularity of services? Yeah, it's more often, unfortunately, than you think. Because if we don't pay attention to it, do you want to see what happens if we don't pay attention to it? Let me show you what happens when we don't pay attention to service granularity. Are you ready? Watch this. This, wait, where's my mouse? Here it is. This guy right here is the JDepend diagram for Struts 1.0. Now, let's pretend for a minute that all these components are services. And that's what our service communication currently looks like. You know, there's only one service point here, but this one there's 3 services talking to this. This is dependent on 2 others. You know, we have afferent and efferent coupling levels. This is not great, but sometimes unavoidable. However, watch what happens, to your point, as we start adding new functionality to the application. You know what happens? This is what happens. This is the actual JDepend diagram, the actual snapshot from Struts 2.0. Are you ready? There it is. And that's exactly what happens. It's perfect at the start and then looks just like that. So the point is, yes, paying attention to this flow and continually this. Now, to avoid this mess, what I typically do as an architect is always pay attention to the granularity, always pay attention to inter-service communication. You know, this I can tell you firsthand. As a matter of fact, Matt Stein, who's in SD1, will tell you the exact same thing. He's also doing a lot of work in microservices. We both see the same problem. Dependencies. Not only transitive dependencies between services, but any sort of service dependency. It's just kind of entropy. You know, we have all these services fine, and all of a sudden they all start talking to one another. And this will happen. So what I usually do is I observe this, and I will go through and say, well, we need to do a service consolidation or a service split pattern, very common refactoring patterns. I will add that as technical debt onto our stories. And I will coordinate closely with the product owner to prioritize those. Which one's most important? Where are we having issues of performance? When I start to see timeouts occur, this is a really good indicator of 2 things. I'm having database problems, which we're going to talk about towards the end of the class, or number 2, I've got too much inter-service communication and I haven't been paying attention to it. I got really excited in a talk yesterday in Hall B about, I was sitting in there watching a talk about service mesh and stuff, and I just wanted to see the speaker's perspective on it. And I was really pleased with it. It was a short 1/2 hour presentation, but I was actually really pleased by it because he actually demonstrated this exact problem. And my point is, what is my point now? What was I talking about? The dependencies, yes. So the point being, I'm trying to remember what I related to now. You know, I hate when I start to think about something and my brain just kind of went off, started thinking about the current. Right. Oh, yeah, thank you. You got me back on track. Oh, I owe you a book if I had one of mine. Download it, it's free. But anyways, so there you go. Yes, thank you so much. Yes, here's the point. He showed a diagram of service dependencies from Netflix and Twitter, and it showed very similar to this diagram that I showed you earlier. Do you remember right before lunch I showed you this guy right here? This is the diagram he showed, but it showed all the services and all the communication points, and I went, oh, this is fantastic because I know of no tool in existence that you can use that will show you service dependencies. Services calling other services. And I got really excited. And so I ran up and said, that was a great session and stuff, and he had all sorts of other questions, and I didn't want to kind of hog up his time. So I went out and talked to 3 other attendees, and I said, hey, what was that tool That was a great tool. And he said, oh, no, that's just, that's D3JS. It was a way of rendering the data. But he said, that was all kind of static data. I'm like, deflate. No, I know of no tool that will do this. I've done this custom by actually looking at runtime dependencies. See, the problem is, if all of you are services, how can I possibly run a tool to find out who's talking to who statically? I can't. There's nothing, because it may be gRPC, it may be a RESTful call, it may be a messaging call. I don't know. And but I can track runtime calls, and I can start accumulating all those runtime calls and actually build the data and put it into D3JS and get a nice graph. I mean, it was all three-dimensional. It kind of looked like the Death Star, and that's what he described it at. It was really cool looking. But it was all raw data that had to be fed in. That raw data capture is what I'm concerned about, because runtime-wise, I'm not capturing every single request that's ever made. There may be hundreds of requests just waiting to be called that are doing all this chaining around. And so it's runtime analysis, which is close, but not 100%. So anyways, that was the point of that whole thing, is this is hard stuff once we move to microservices, managing the dependency matrix. Going back to Struts 2.0, going all the way back here, is exactly what will happen. Right here. Exactly what will happen to your ecosystem if you don't try to govern and control this. This has nothing to do with source code, everybody. This has nothing to do with Kubernetes. This has nothing to do with whether we should use Spring Boot or Drop Wizard. No, this is the fact that things will fail all the time, regardless of how well you code it. That's how important architecture and design piece is. The coding piece is obviously important. So yeah, that's why that whole loop is continuous. Probably one of the most important slides that you can absolutely take away from today is probably this guy right here. Perhaps the most important slide, probably in my entire deck, is this guy. So you have the PDF. So you can copy-paste this slide out, but this is the normal. Oh yeah, so back to this. So I record this technical debt and then work to find out these dependencies, and then to refactor, to do service consolidation, or even a new database domain. And I usually try to schedule those at least within a couple of iterations from the problem. But, whoops.
Other than inter-service communication, any other metrics that you should track?
Oh yes, lots of them. Let me see, we're way off on tangent. But I want to answer your question, though. What time? Let's see, it's 3:15 that we end? Oh, 3:15 is our break. Is that right? Okay. Let me answer this one question and kind of get back on track. What was your question? I hate getting old.
What other dependency, or what other
Oh,
metrics?
yeah. Okay, so what other things? Let me show you let me answer your question. And the question is, okay, so besides inter-service communication, what are the other things we should be watching for? Can I table this? Because I want to show you that exactly now, but I don't want to I'm going to get too ahead of myself, and I realize if I start describing things I haven't shown you. So, analyze arc. All right, so let's keep a list, everybody, okay? So the question is this: what are the things, by the way, that we should be looking at as these pitfalls, as the things that will create? Might help if I showed a slide, wouldn't it? Mark. Okay. What are very, 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 very good and important question. What are the things that I should be looking at besides inter-service communication to make this thing work? The pitfalls and anti-patterns that you talked about or asked about. All right, so let's keep a list, everybody, because we've got little notes in our book, and I'm going to keep the list as well so that we can actually review it. Okay, so the first is inter-service. Boy, we got a long way to go. All right, so that's number one. Inter-service communication. Okay. Number 2, which I can also mention right now, shared libraries. That's number 2. The more shared libraries you have, we're breaking the bounded context, and things won't work. Okay, so shared libraries is the other thing that, as an architect, I am going to pay close attention to. This will happen as well. Okay, so, and when I say a shared library, I'm talking about those jars and DLLs that contain our code, the formatters, the interceptors, or not interceptors, annotations and stuff. So shared libs. Okay, so there's 2 so far that we have. I'm going to show you 3 others, but I want to explain them first before I show them to you. All right, as a matter of fact, let me show you. Yeah, there's our ecosystem. Yeah, all right. Let us actually get to the real. We're going to roll up our sleeves. My sleeves are already rolled up, but we're going to roll them up even further now, because let's get into the real nitty-gritty of service communication. This is the hard stuff. Notice I've been showing all these services communicating to one another. As I showed you this morning, that's not really how things work. I want to show you 6 different topics here. We're going to actually analyze REST, RESTful calls. That is the de facto standard. We're going to look at REST, but also see some of the issues associated with REST. Let's take a look at messaging as well. Can we use messaging in between all of the services when we communicate? Absolutely. What are some of the implications? How do you do it? What are the problems? What are the benefits? We'll take a look at that. I want to show you gRPC, Google's remote procedure call. This has been kind of a trend. This is another one of those trends that seem to be appearing, shiny new thing that we need to use. I want to show you that as well, and not only show you how it works, how to do load balancing with it, but also when you should use it. Now I want to talk about gateways. Now we get the chance to talk about, hey, can we use a gateway to orchestrate all this stuff? And what should we use these for? I'm going to talk about cross-cutting concerns right within here. That's another thing. Let me check that off on the list here, because I'm going to talk about cross-cutting concerns and also workflow. I'm going to talk about orchestration and chaining within here as well, and the cross-cutting concerns. And I also want to talk about 3 patterns. The orchestration pattern. How do you do orchestration in microservices if we don't have a conductor? Well, we hire one. And so we'll take a look at the orchestration pattern. I want to show you reporting. How do you do aggregation within microservices if I need to do searches or things across microservices? And how do we communicate microservices to existing COBOL mainframe systems or older systems that we're planning on converting later? Okay, and so those are all the things I want to show you. Now let's start actually with REST. So with REST, here's our situation, because I want to show you all these with an actual example. Here's our customer wish list right here, and here's our customer demographics. The example is, I need your name. I need the name of the customer. Well, how do I go and get it? Well, Mark, just make a RESTful call to the demographics. Which instance? Oh, yeah, that's right, huh? I could talk directly to that service. 100 milliseconds round trip, remember. But the problem is there's multiple instances. So what really happens is this. As I showed you before, and now we get to actually describe this. What really happens is I go through all of my infrastructure. I have to go through the gateways in order to get to that, because then I have load balancing. I know which service is responsive, which service is ready to receive my request, which one's the healthiest. That's the one I want to pick. Okay. All right, so the point is I need to go through this endpoint in the gateway, which then goes to this endpoint in my proxy, which goes to the endpoint that's actually exposed through that service in Docker itself, or Kubernetes, whichever one. All right, so let's analyze this. If I use REST, RESTful communications, here's what happens. I need to communicate. There's 3 problems that occur. As a matter of fact, there's more than 3, but I'm going to show you 3 problems that occur with REST. That's 100 milliseconds. But then it also takes 100 milliseconds to get from the API gateway down to the service. So is our RESTful call actually 100 milliseconds round trip? Nope. It's actually 200. And as a matter of fact, add a load balancer in front of that, and now it's 300 for every request just to get the name. So you know those arguments, which I'm sure many of you have probably had. I can give you some ammunition. Maybe. Which is faster, REST or messaging? Oh, I get so bored of that conversation now. You know why? Because here's what happens. We start arguing about it. You can't Google that because it depends. But it's something that's like, oh, REST is always faster. No, messaging is actually faster. You know, let's just try it in our own environment. And you know what the problem is? We do a POC. And so here's what happens. I do a direct RESTful call over to Manoj. What's that take? 87 milliseconds. Now let's try and that's tuned. And let's try now a tuned message call. So that was 87 milliseconds. Let's do messaging. You know what it shows up as? 92. 87 to 92. Okay, so it's 5 milliseconds faster in our environment to use REST. Told you REST was faster. However, that's our POC benchmark. Whenever you get into this argument, do this in an exact environment that you have with prod. Because, in fact, with messaging, it is not going through those gateways. So, in fact, it is 92 milliseconds. What's REST? 200, maybe 300, maybe 400, depending on how many gateways and hops. So don't fall into that trap. And so that's one of the ways of kind of qualifying that. But anyways, we've got latency here, so that's problem one. Maybe not. There's ways of dealing with the latency, but that's kind of a maybe. But this problem is very real. Okay, so here's all my endpoints, my well-defined endpoints on my gateway or my proxy, it doesn't matter. These are all the public endpoints of the functionality that I expose publicly for public consumption. Okay, so I need the name. What endpoint am I actually going under here? It's called an endpoint called customer info. Get customer info, that's the endpoint. What is that endpoint returning to me? It's returning to me a JSON object that's 500K that includes every bit of information about that customer. What do I want? The name. Fallacy number 3 of distributed computing by Peter Deutsch. Bandwidth is infinite. That's why it's a fallacy, yes. You know, one of the mistakes that we start making is in our monoliths, do we have to worry about bandwidth? No. We get to our application and there's no network communication now. It's to get to the application. But now, look at everybody here in the room. Just look around. We're going to all intercommunicate together. Boy, is that going to stress out the network, isn't it? But bandwidth is infinite. This is a form of coupling called stamp coupling. It's called stamp coupling, and I'm not sure why. You can Google the stamp coupling just to find out the name. I don't remember the history of it. But here I can describe it for you, though. Stamp coupling is a form of coupling where you are returning me all this information, 45 distinct pieces of information, including the person's picture. And in fact, all I'm doing is pulling off just the name. It's a form of coupling because, not if, but when this endpoint contract changes to add, let's say, an alien status code or maybe an address line 5. Do I care about either of those two fields? No, because I'm just a customer wish list who wants the name. But guess what? I have to conform to that contract version at some point, which means I'm going to have to do a redeploy and possibly change my code when I don't need to. Stamp coupling. So that's first problem, is eventually I'm going to need to change my code when I don't need to. Problem number 2 of stamp coupling. I need 200 bytes of information. But what is this customer demographic service giving me? 500K for every request I make. It will slow down your network. It will. Maybe not for 10 services, maybe not for 20, but once you get more services and more inter-service communication, your network will slow down. The bandwidth is not infinite. So 500K versus 200 bytes. Okay, so that's problem number 2. That's problem number 2. But here's what we want to do. We want to avoid stamp coupling. Oh, you know what, Mark? That's probably why we're having network issues. Touché. Thank you. And so what do? You go back to work, and what do you want to create? I want to create my own contract.
Hello, Mark. One question.
Oh, there we are.
Hi.
It sounds like it's coming from above. That's why I keep looking up.
Yeah, the question is that during the communication channel, are you not considering the latency of the cache if the data is available in the cached memory? Your communication process time will reduce, or in the sense the response time will be faster. So considering that, can't you predict the latency in the production, or including gateway, load balancer, and everything?
Yeah.
Worst case would be excluding the cache. Best case would be including the cache.
Which cache are you talking about? Are you talking about as cache in the service?
Yes.
Oh yeah, no, that's so caching data in the service, which we're, by the way, we're going to talk about in part 4. Caching is a way of increasing performance, absolutely, and it's also a way of being able to share data, as we'll see, which is really cool. However, it will not do anything for what we're talking about here in terms of network bandwidth and latency. Yeah, caching will be able to overcome a latency issue by not having to go out to the database. It's an in-memory call. But I still am transferring 500K across that wire. And so yeah, the answer is no. Caching will not address this issue. We still have latency and we still have bandwidth that we're going to deal with. But I find your question very interesting, though, because if we start having bandwidth issues and performance issues, one way to address that is to add caching. But the problem is we're looking at the problem entirely the wrong way. That's not the solution. You see, it has nothing to do with the performance of the microservice, which we will be faster, and we may overcome that, but the root cause is this problem of stamp coupling. So solving that, we want a get name endpoint. Get name, 200 bytes, my own private contract, my own contract, that I don't have stamp coupling now. So I've just solved stamp coupling. And you know what I've done? I've increased or decreased the network traffic significantly, which means I generally will increase the overall performance of my network, which is going to be faster than faster communications. But you know what the problem is? You see these endpoints right here? Watch what happens to our APIs. That's what happens. 1,200 endpoints that we have in our Swagger documentation all of a sudden becomes 4,500 endpoints. And it becomes so polluted with inter-service call contracts like get name, get zip code, get alien status code, get first name, get last name, that we have no idea what to call.
Yes. Can we use a GraphQL in this case?
GraphQL is one way. I'm going to show actually GraphQL applied when we start using the orchestration piece. But yes, GraphQL is one way of actually abstracting that contract. So yes, it is one way of being able to reduce that communication point. GraphQL is adding a level of abstraction because now I'm able to have a variable schema, but it also handles a level of orchestration as well to get that data. So it is one place, I'll say, where it possibly might apply. Yes, it's a good observation to help solve this problem, but I'm going to show you an even easier way so you don't have to use GraphQL. But this is one applicability to GraphQL. I'm going to show you a second applicability of GraphQL in a little bit as well. So here's the problem, though. While we solve one problem of stamp coupling, we introduce another problem of over-polluting our APIs. Well, what we want is a private API. Well, let's create a private API. Please don't. Because what I have to do is take my entire infrastructure, my load balancers, my gateways, and my proxies, which all have licensing costs, by the way, and maintenance, and I have to duplicate that functionality to another subnet. And that's where my Interservice goes. From experience, it's a disaster. Why? My costs of transport now doubled. My infrastructure is doubled. Number two, the only thing that makes it private is that it's in another subnet, which anybody can get to. And the governance is